Okay, so we're going to go now, we're here at the table, and let's break down our sources of variation, first starting with regression. So we have sources of variation in a given scatter plot, and first we could talk about our sums of squares with regard to the summation of our y sub hat I minus our y bar. Write that a little cleaner there. Squared. So this is the distance from our individual points on a line all the way back to the overall mean. So maybe to match up with this here, I'm going to rewrite this in pink, just to make it clear what we're talking about here. Okay. So I have variation that is the distance from the line to the overall mean. How much difference from the mean do I get? Then I have my error term. And my error term took my individual points and said, how far are those individual points away from my line? How far are my individual points away from my line? And in the case of what I've drawn here, that would be in black, just to keep them straight. So this is going to be my least squares, and this was going to be my actual y sub i's minus my y hat sub i's squared. Move this over because we don't need it for a minute. Okay, so that's where I got that variation there. That was my least squares, and that is minimized in least squares regression, but it's the error that's left over after we've estimated where a point should be on an x-axis given our line of best fit. There's some error where the points don't fit perfectly on that line. There's some error, and so they're separated from that line a little bit, and that's calculated here. We've tried to minimize that error in having a line of best fit by definition. And then we had our overall estimate of where things should be based on a y bar, or an estimate of the mean in this case. And we can look at that as the summation of our individual y sub i's minus y bar squared. And this looks a lot like our variance equation. When you first looked at a variance equation, you may have looked at this in terms of x sub I and x bar. That's because we were only dealing with one variable at the time, so we call it x. Now, because we have a x and a y, we're going to read this in terms of y's, because y is our response variable in this case, and in the case of regression. So these sums of squares look a lot like what you put into a variance equation, which you remember that our old variance equation would have been something like the summation of x or y, it doesn't matter. Let's use y for consistency, y sub I minus y bar squared, and then you'll remember we divided by n minus 1 because we had degrees of freedom, right? So that was how we calculated variance, and then we used that to measure our other, come up with estimates of our other summary statistics. Well, accordingly here, we have a degrees of freedom that's associated with each of these estimates of variance. And those degrees of freedom are important. They tell us a lot about, they allow us to calculate some kind of averages, and they tell us about how much freedom to move we have in our estimation of parameters. So more on that later. For now, our degrees of freedom for our regression are generally, in this case, going to be 1. Our degrees of freedom for our error term are going to be our number of samples minus 2. Okay, and our total degrees of freedom is going to be just like it was before, n minus 1. Okay. So this has to do with how many things we've already estimated before we've calculated these sums of squares. So how many things do you already have to assume are held constant in the equation? That's where we get our minus. So in this case, minus 1, because we've already calculated a mean. We're assuming that mean's there. So we had to do that. So we don't just have n amounts of ways the data can vary. We have n minus 1 because the mean is held constant. Think of it as if you had 10, you had a number that is a known value, and you have 10 samples. Those samples can be anything for the first 9 samples, but in order for that mean to get the same mean, that last 10th sample is fixed. It's held constant in order to come back to the same mean. If that's confusing, we'll come back to degrees of freedom in just a second. So, but what degrees of freedom is a stand-in for is it's essentially how many things you have sampled. And so here the sums of squares obviously goes up the more items we have to sample, and so we want to divide by that to get what we call our mean squares. And so in this case, our mean squares is just going to be our sums of squares divided by the degrees of freedom. So here it's going to be our sums of squares regression divided by 1. Here it's going to be our sums of squares error divided by n minus 2, right? And then we of course could have a mean squares total, but that would just be our variance, right? So we already know that that's interesting. Often these will be replaced with we'll abbreviate these, and instead of showing this whole equation, we'll just call this MSR, and we'll call this MSE. Let's move our F over here. Okay. So why that's important is that it turns out if you take a ratio of the MS regression to the mean squares error, you can use that to calculate some pretty interesting things. In particular, we can use it to calculate what's called an F-score. And that F-score has a probability associated with it. Okay. So, we can come back to that in just a second. I also want to point out where our R-squared comes from. So, if our regression is a large proportion of our sums of squares total, then we can say that a lot of the variation in the data, the total variation in the data, is explained by the regression. So where does R squared come from? In this case, we can actually use our sums of squares regression and our sums of squares total to estimate the strength of our regression. Sums of squares regression divided by sums of squares total can give us our R squared. So all we have to do is take a ratio of those two things. That's kind of a nice thing to be able to do. And once you get a handle on understanding the sums of squares here, you realize that the reason that we've called this an analysis of variance table is that we have all of the sources of variance laid out here, and we can really analyze where the variation is. Similarly, if we have a really good regression that wouldn't be due to chance, we would expect that the sums of squares due to error would be minimal compared to the sums of squares related to the regression. The regression would take up more of the weight of explaining what's happening in the data. And so as these points get closer and closer to the line, we minimize the error term, as we minimize that error term and the line itself is farther away from the overall mean, more of the total variation in the points is going to be associated with the distance from the line to the mean, and less of the variation will be left over as error. That means when we calculate our total, it's going to start looking more and more like our regression line. So, in our little example here, if we were to redraw this for a set of points that were closely associated with the line, let's have a set of points that's right next to the line, like that. These points still have a mean associated with them, so there's still a y bar, but the distance from the line to y bar starts looking an awfully lot like the distance from the points to y bar. So the distance from each of these points to y bar starts looking very similar to the distance from the line to y bar. Where do we calculate the distance from the line to y bar? Right? This is the distance from the line of best fit to y bar. Where's our total? Our total is the distance from the points to y bar. As the distance from the points to y bar starts looking like the distance from the line to y bar, these two numbers become similar. As those two numbers become similar, the sums of squares regression divided by the sums of squared total starts to approach 1. And as that approaches 1, we're saying the proportion of our variation associated with the regression line is coming close to being perfect, or it's a high value. On the other hand, if the data is really messy, the reverse will happen, and we'll have a small amount of our sums of squared associated with the regression and compared to a large amount in the overall data set. Okay, finally. So that's what we can do with sums of squares, and that's how it's related to that all-important R-squared value, which is a measure of strength in our data set. Let's clean up this board a little bit.